Do you ever wonder how your computer manages to run so many applications at once? The magic behind it is a concept called demand paging. In the realm of modern operating systems, there's a memory management scheme that's been quietly working behind the scenes, making your digital life more efficient. This unsung hero is demand paging. It's like the backstage crew of a theater production, ensuring everything runs smoothly, even if you never see them in action. At its core, demand paging is about optimizing memory usage. It's like a wise old sage, knowing that we don't need everything all at once, but only when we ask for it. Thus, instead of loading all of a process's pages when the process is initiated, demand paging loads pages from disk to physical memory only when they're needed. This technique significantly boosts the efficiency of memory usage and allows systems to run applications that require more memory than what's physically available. Now, let's take a moment to understand the key components of demand paging. First, we have virtual memory. Think of it as a temporary storage area where pages of memory can be mapped out of physical memory to disk storage. Second is the page table. This is like a directory, holding the mapping between virtual addresses and physical memory addresses. It's a traffic controller of sorts, directing where pages should go and indicating whether a specific page is in memory or needs to be fetched from disk. Then there's the swap space. This is a designated area on the disk where pages from memory are stored when they're not currently needed in RAM. And lastly, we have the page fault. This is an interrupt to the processor triggered when a program tries to access a page that is mapped in the address space but not loaded in physical memory. In essence, demand paging is like a diligent librarian who only brings out the books you need when you ask for them, instead of overwhelming you with an entire library. It's a remarkably efficient system, making our digital world run more smoothly than we could ever imagine. Now you might be asking, how does this demand paging work? Well, let's dive right in and explore the steps involved in the operation of demand paging. Imagine you're in a vast library, but you can only hold a few books in your hands at once. These books are like the pages in our memory. When you need a specific book or page, you look for it in your hands first. This is the page reference step, where the system checks the page table to see if the page containing the needed address is in physical memory. But what if the book you need isn't in your hands? That's when you have to go find it on the library shelves. In the world of demand paging, this is known as a page fault. The system realizes that the page isn't in memory, so it sends a signal to the operating system to fetch the required page from disk. Now, suppose your hands are full, but you still need to pick up another book. You'll have to put one down first, right? This is akin to the page replacement step. If physical memory is full, the operating system has to decide which page to remove. Using algorithms like least recently used, first in first out, or the clock algorithm, it determines which page to evict. Once you've decided on a book to put down, you place it back onto the shelf, making room for the new one. This is the page swap step. The chosen page is swapped out to disk if it's been modified, making room for the new page. The new page is then read from disk into the freed frame in memory. After swapping the books, you update your mental note of which books you're holding. In demand paging, this is the table update step. The page table is updated to reflect the changes, marking the new page's frame location and updating any necessary status flags. Finally, you can go back to reading your book. In demand paging, this is the restart instruction step. The instruction causing the page fault is re-executed, but this time the page is in memory, and execution continues normally. So, just as you can manage to read numerous books in a library without carrying them all at once, your computer juggles multiple applications without breaking a sweat. It's all thanks to the magic of demand paging, a clever technique that makes the most of limited memory resources. And voila! That's how your computer juggles multiple applications without breaking a sweat. You may be thinking, that sounds like a lot of work. Why not just load everything into memory? Well, there are several advantages to demand paging. Firstly, demand paging promotes efficient memory use. By only loading the pages that are needed, it reduces the physical memory required per process. This is like hosting a dinner party and only setting the table for the guests who RSVP'd, rather than for everyone you invited. This way, more processes can be loaded concurrently, much like being able to invite more guests because you have more space. The second advantage is reduced I/O overhead. In the context of our dinner party, imagine having to cook every single dish on the menu, even if nobody ends up eating it. That's quite a waste, isn't it? Similarly, by avoiding the loading of pages that are never accessed, the number of I/O operations is minimized, saving valuable system resources. Thirdly, demand paging supports larger applications. This means that it enables applications to run that are larger than the available physical memory by swapping pages in and out as needed. Going back to our dinner party, this would be like being able to serve a 7-course meal in a small apartment by bringing out each course one at a time, rather than trying to fit everything on the table at once. These advantages significantly impact the performance and capabilities of a computer. Efficient memory use allows the system to handle more processes at the same time, enhancing multitasking capabilities. Reduced I/O overhead helps in maintaining system speed and responsiveness. And the ability to support larger applications means you can run more complex software, even on systems with limited physical memory. So, while the process of demand paging might seem a bit complex, the benefits it provides are well worth the effort. It's like having a well-organized and efficient kitchen that allows you to host a successful dinner party, where every dish is served hot and fresh, right when it's needed. In short, demand paging makes your computer smarter, not harder. Like all good things, demand paging isn't without its challenges. Firstly, let's talk about the performance impact. Handling a page fault is no small task. It requires disk input and output operations, which are considerably slower than accessing memory. When a program experiences frequent page faults, the system can spend more time servicing these faults than executing the actual program. This condition, known as thrashing, can severely degrade system performance. It's like trying to read a book but constantly having to go to the library to fetch each page. The back and forth becomes the main activity, slowing down the reading process significantly. Now, onto the second challenge, complexity. Demand paging isn't a simple memory management scheme. It requires sophisticated algorithms to decide which pages should be loaded into memory and which ones should be swapped out. It also necessitates an efficient method of handling page faults. All these elements add layers of complexity to the design and implementation of the operating system. It's like playing a game of chess, where each move, each decision, has far-reaching implications and requires careful thought and strategy. Moreover, these complexities aren't isolated. They interact and influence each other. For example, the choice of a page replacement algorithm can dramatically affect the rate of page faults and thus system performance. Similarly, the handling of dirty pages, those modified while in memory, also adds to the complexity and can impact performance. But let's remember, these challenges aren't insurmountable. They are trade-offs, considered and managed in the design of modern operating systems. Engineers constantly work on new techniques and strategies to minimize these effects and maximize the benefits of demand paging. They strive to maintain a delicate balance, ensuring efficient memory use while keeping system performance at an optimal level. So, while demand paging is an ingenious solution, it's also a delicate balancing act that requires careful management. So now you know all about demand paging. It's this ingenious memory management scheme that our modern operating systems use to make the most out of our computer's physical memory. It's based on the principle that programs often use only a small portion of their total code and data at any given time. By loading only the necessary pages into memory, the system can minimize the amount of RAM used per process, allowing more processes to run concurrently. It's a clever dance of page references, page faults, page replacements, page swaps, table updates, and restarting instructions. It's a system that allows for efficient memory use, reduced I/O overhead, and the capability to run larger applications. But it's not without its challenges. The performance impact and complexity of demand paging can be significant. Remember, next time your computer runs smoothly while multitasking, you can thank demand paging for that magic.